we stopped when we were looking at another modality of search, which is called breadth first search. And the strategy here is to expand the shallowest node first, okay? The one we're still assuming that the cost of jumping from one node to another, it's just the cost of one. And so we are looking for the shallowest node first. We're looking for the uh, shortest path from the start to the goal. And this time, this all the procedure keeps the same, except that we change the structure. The data structure in which we keep the fringe is now going to be a FIFO queue, a first in first out queue, an ordinary queue, not a LIFO stack, but but a FIFO queue. Okay, what are the consequences of that? Well, the if we start the first if the starting node is S, well, that will be the only node on the fringe in the beginning. So when it is expanded, we get D, E, and P. And when they are stored on a FIFO queue, we process them one after the other. So we process the first one. Let's say the first one to appear was D. When taking D out of the fringe, we expand D. That is, we find the successors of D, and the successor states are B, C, and E. Okay. Now we have a fringe that is bigger. It contains B, C, E, E, and P. The next step would be take the other element uh, from the fringe. Which element are we going to take from the fringe? Try guess. Just we are storing we store the EMP on a FIFO queue. So that means that if you want to see that, if you couldn't answer the question, is that you're not really understanding this very simple method. But look, let me backtrack. So here is S, we expand S and we get, this is the queue, okay? So D comes first. So this is the in part of the queue. And this is the out part of the queue. So, okay, there goes D, then E, and then P. That's the order in which so when we expanded the node S, the first one we stored on the queue was D, then E, then P, okay? So then we take one node out. Which one would that be? Well, D needs to be out. So we take it out of the queue. And what happens when we do that? Well, when we do that, then we expand D. So now D is expanded and we discover these other three nodes, B, C, and E. And as soon as we expand the node and we discover the successors, we store them in the queue. So then we would store B and then C and then E, okay? So, and we are done with D. And then we repeat the process. Take an element from the fringe, which means from this data structure. This is, the fringe is stored in this data structure. So the next one to be taken out or expanded is E. Okay, so E gets out of the queue and it's expanded. So we get H and R, and HR are going to be, well, posted on the queue behind the other elements. And we continue the same process. Okay, so then we take P out, discover its only child, put the child in the queue, and then go to B, which is the next one in the queue, and so on. So you should be uh, able to do all this, okay, and to know which other, to see why are we getting the nodes that we are being expanded. When we look at that from a little bit afterwards, we see that during the first round, we expanded D and then E and then P. And then only then we started expanding nodes at the second level, which are the children of the children. And we expanded B and C and E, and then H and R, and then Q. And we did all those that are 2 hops away from the beginning, from the starting step. Then in the next iteration, we would expand these other nodes, which are in the third level, and so on. So this is a search in tiers where we do not expand any node until we're done with the first level, with all the nodes in the previous level. Okay, we do not expand any node in a given level until we're done with all nodes in that same level. How do we program that? How do we take care of that? Just keep the same search procedure, only store store the elements of the successors that are being discovered on a FIFO queue. If you use a LIFO stack, then the result is you would be doing a depth first search, not a breadth first search. Okay, so we already studied the first one. Let's take a look at the theory of this breadth first search, or BFS, and what are the properties. Okay, so which nodes are expanded by BFS? Well, we know they are expanded in this fashion, level after level. If we have in our abstraction of the problem, we have the starting node here, and we have a constant branching factor of B, then at the first level we would have B nodes, and the second level we would have B squared nodes, and so on, powers of B, until we reach a goal. Okay, then when we reach a goal, the algorithm stops, and then we have found the shallowest solution, which means the one that is closest to the starting node in terms of hops. How many levels down? Okay, so if we are only considering traversals or hops from one node to another, then we discover the goal that is in the shallowest position. And let's say that in a particular problem, that goal is S levels away from the start. Then we would have B to the S nodes on that level. So if you add all of the nodes, and we consider that we are counting the nodes, because that's when we discover the nodes, that's when we do the most of the work, and that's why the way we compute the time complexity. So if you add 1 plus b squared plus until bs is more or less b to the s. So in fact, if this is a regular tree, let's say a binary tree, you would have in the last level one more node that you would have in the rest of the tree. That's why the big O is true, because it's only twice the number of it's a constant times the number of nodes you have in the last level, which is b to the s, by the properties of trees, of binary trees. So that's why we take b to the s, which is exponential and not very good. But let's say, what is the complexity of the memory complexity? That means how big is the fringe? So since the fringe is roughly the last tier, we may have a few nodes in one level and a few nodes in level below, but they are contiguous. They are almost the same level. So it is approximately b to the s again. So that's the complexity for the space complexity for BFS. Now, is it complete? Which means, does it find the goal? Yes. If a solution exists, it will definitely get there, because it keeps exploring all nodes, all nodes, all nodes. And if there is a goal, it's going to reach it. And if there are many goals, it's going to reach the first one, the shallowest one in terms of distance from in hops from the start to that given node, that given goal. Is it optimal? I mean, does it find the best solution? If your best solution, if your definition of the best solution is the shallowest one, yes, it does, of course. And if it has one, and that is, but that means that the costs are all one. That means each hop costs you 1 unit, and all hops cost the same. Uh, but that can change in another setting. But if this is a setting, then yeah, the algorithm is complete, it's optimal, and it takes exponential time and exponential space complexity. Now, they do have some advantages and disadvantages with respect to each other. When would you think that BFS would outperform DFS and vice versa? When is a breadth first search is just like, oh, I'm exploring level after level after level. When is that better than exploring depth first search, going deep, 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 and then backtracking and deep, 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 and backtracking, backtracking, backtracking? When is it? When would BFS outperform DFS? Can anybody give me a little example?
Would it outperform when there's like two long branches?
Oh, okay then, yeah. Okay, so you would have, let's say, this is the cartoon again. And where would you place the goal? So let's say this is the start node. And where would you place the goal? If you, where would you place the goal to, in your example?
On the right side.
On the right bottom?
Yeah, bottom right.
Bottom right?
Because yeah, depth first search would search all of the left one and then all of the right one. And with breadth first searching each row one after the other.
BFS would explore all of the nodes. That's like the worst case. And DFS will also probably be doing an equally as bad search because it would reach also this node at the end. This is not perhaps a good example in which they both perform as poorly. They both perform as in the worst case. So how can we place the, where should we place the goal?
Top right.
Or no, what happens if you place it here? Then how does BFS outperform? Uh, Goes here and chooses another uh, child and another child of child, another child of child, and finds the goal if the goal is there. Okay. Whereas if we do DFS in green, it would be doing first level, almost in second level, almost in level. So we would reach the goal, but obviously BFS would outperform DFS.
Isn't it the other way around? Isn't BFS?
Oh, sorry, that's right. Yes, right. You're right.
So the
Yeah.
goal would be on somewhere on the right, like top right, for BFS to outperform DFS.
So this is when DFS would outperform depth research, would outperform BFS. That's right. This is the case. How would we draw the example for the other case? Where would you place?
The goal would be the top right.
The goal would be in the top right, like, okay, somewhere over here. Okay.
Sure, yeah.
Then, okay, that's exactly right. Because then what would BFS do, which is it would perform all this. So it would be too much, too long, and it would take too long. Whereas depth first search would reach it in a few steps, okay? And so this is the case. Thank you very much for clarifying. So these are it's necessary that we realize when one outperforms the other. And here we have, for example, a problem in which we have different depths of in the water. And this is a uniform. However, in this case, it's a uniform depth. And let me know. which algorithm is running here? Is it depth first search or breadth first search, D or B? Okay, so what's the answer? Please write that in the on the chat. What is this? Okay. Well, the answer is depth first search. D as in doing. Why? Because look, the exploration is of this fashion, sort of going in concentric circles, opening and 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 opening until you discover the goal. Once you discover the goal, you have the path to the, you find the path to the goal, and that is that is what you can do when you use depth first search. By the way, be aware now that of an important fact. When you code these algorithms, your answer will, or the output, the outcome of your program will not be the goal, will be the path. We need this path. So you should be doing whatever is necessary to keep in memory all the choices. So as you you open and you find a lot more and a lot more options and a lot more options and a lot more options. And for each time you open a new level, you choose the best one. And each time you choose, you open the next level, you choose the best one, and then so on. So you're building this path until you reach the goal. Then what is this algorithm? Write it on the chat. Let's see. This.
Can you play the video one more time, please?
Yes. There you go. Again. Okay, so what's your answer? It turns it's BFS, breadth first, depth first search, DFS, this one, DFS, depth first search. How do we know? Look at the exploration. It's not opening concentric levels or nodes that are at the same level. It goes like immediately to the next, the child and the child of the child, and in this fashion. When it stops here, it backtracks and starts another route here, and so on. Okay, so this is this is actually depth first search.
I'm a little confused. So were they both depth first search, or was
No,
the last?
No, the first one was the first one was breadth first search.
Okay. Yeah. I think I misheard you.
Sorry. Yeah, this is breadth first search. This one, because you see that it's opening level after level after level, and that is breadth first search. Sorry, okay, breadth first search, and this other one is depth first search. Okay, so there's how to combine the, is it possible to combine the advantages of both of them? It turns out there is a strategy that allows us to do that. And the answer is yes. And we need to combine them. We do that, for example, by steps. You run depth first search with limit 1. Okay, so you run a very short DFS, depth first search, and if you find no goal, then you increase the number of levels. Now you do DFS again with 2 levels, and then with 3 levels, and if you find no goal, you keep on doing it until you find the goal. Okay, so you would say, well, that's very redundant. How can it be advantageous? But what happens is that most of the work, most of the repetition is done in this part of the tree, which is very shallow. Remember that the upper part of the tree is very shallow compared to the whole number of nodes that can be expanded. So even if you do this repeated number of times, you would be exploring less nodes than if you had to explore them all in a bad DFS or bad BFS or in a brute force search. So that's why this strategy is not so bad. And there is also another kind of search that is when we have more information, when we have a cost of when jumping from one node to another. Okay, in this case, mind this graph is directed. So for going from the start to D is possible, but has a cost of 3 units. And we can go to E at a cost of 9 and to P at a cost of 1. But then we would like to find the shortest path to the goal in terms of these costs. Okay, so we are looking for the least cost path. And so this leads us to another strategy for searching, which is called uniform cost search. Okay, so what is a strategy? Expand the cheapest node first. And the fringe is a priority queue. You should remember what a priority queue is. And the priority in each node of the priority queue would be the cumulative cost, okay? Not the cost of the last hop, but the cumulative cost, the accumulated cost. So, for example, if we start in S now, when we have S in the fringe, and since it's the only element, we expand S, and it has S will always have a cost of 0 because it has no cost. We're already there. So we expand that node. We take the cheapest one is S itself, and we have 3, 9, and 1. So which one will we open next? What do you think?
Next, it should open P, right? Because it's only going to cost 1.
Exactly right. Okay, so you open P, and then you have Q with an associated cost. This hop cost you 16. Okay, but now remember that we need to add here. What is the cost? Which node, D, E, or Q? Those are the nodes in the fringe. So which one will be open next? We need to do a little computation here, because if we want to open Q, the cost is not 16. The cost will be the cost of going from S to P, which is 1, plus the cost of going from P to Q, which is 16, a total of 17. And in the other nodes, we have already 9 and 3. So as you can guess, the next one to be open will be D, and we discover B, C, and E with these costs attached. So what are the costs right now for them that we should consider for the next point? So this was 3 plus 4 would be 7. This would be 3 plus 11 would be 14. This would be 5 plus 3 is 8. And this other remains the same. So which is the next one to be opened? We have a 7, a 14, an 8, a 9, and a 16 on the fringe. I mean a 17 on the fringe. So we choose B, which is less costly, and so on. Are there any questions up here? Because then we do the same thing over and over and over. We consider the cumulative cost, not the cost of this hop, but the cost of getting to a node, okay, getting actually to that node. So that's what we do when how we proceed in uniform cost search. How does it look like when we keep going and going? It has a resemblance to the breadth first search, the one that looks levels after levels, but in a sense, these costs increase or change or vary the distances from the nodes and put them to one or another level. So you see that there are some, instead of levels, we have now these contours that are of a, so the yellow is a small, this yellow, these pink contours, this smallest cost, then comes another contour with the next range of costs, and then another contour with the next range of costs, and so on. And what does that mean for the works of the algorithm? Well, if we have a situation like this where there are goals here and there, so how does it expand? Let's see. Let's say that it will get to some one way. So you explore and explore until you discover a goal, which is the shortest one in terms of costs. This might be available at fewer costs, but these costs are more costly than all these long paths to get to this goal, because we discovered it before we discovered this one. It is because even if there's a longer path here, that is cheaper than the path from S to this other node. So let's say that once we discover a goal, we have explored so many contours. Okay, how many contours do we explore? So imagine that the whole solution has a cost, because we know the cost of the solution, and it has a cost that we call C star. And just to make it possible to do some computation, we should imagine or assume that the arcs cost at least some amount epsilon, okay? Then the effective depth is roughly the cost of the goal divided by the cost of the step. That's how many steps you need to reach the effective the goal. And so you have C star divided by epsilon tiers, and then just repeat the same reasoning in the analysis as in the analysis of the previous algorithms. So the fringe, I mean, the time that it takes all these is just like this amount, the amount of nodes we have in the last tier, on the last level, would be more or less that's the number of levels. But we have this branching factor, and we have b to the 1, b to the 2, and so on. So if we have these many tiers, we have b to the power of those many tiers. That's the number of nodes that we have in this gray area. Then how much space does the fringe take? So that's the last tier, and that would be practically the same. And now, is it complete? That means, do we find the goal, if there's any goal? Well, if the best solution has a finite cost and a minimum arc cost is positive, then it will find. But if you have something like negative costs, then you would find that you can have a cycle, an infinite cycle, and you would never get out of here, because you have to go round and round and round because of a negative value that makes you go, that reduces the cost, and you can reduce any cost arbitrarily. And if you have no finite cost, if you turn to have infinite costs, then also you would never end. And so we need to keep these two solutions a finite cost, and a minimum mark positive cost. Okay, is it optimal? Yes, and the mathematical proof will be made when we get to another algorithm called A star. Okay, now uniform cost has its issues. Let's see, what time is it? Oh, so uniform cost has these issues that it explores increasing cost contours, and so the good is that it is complete and optimal, but the bad is that we're still wasting a lot of time because we sort of explore in every direction. There's there's no way that we favor any direction and or any information that we may have about the goal location. It is like this scheme. You see, you take a wide shot and explore all these nodes, and then another wide shot and explore all these nodes, because this uniform cost is also a version of depth first search. Can we do better? We would like to do better. Like, for example, if we had some information that the goal was somewhere in that direction, then we would expand only the nodes included in the blue ellipse, and then we would be wasting less time. So this is exactly, this is how UCS looks when all costs are the same. That's why it says empty UCS. So when uniform cost has the same, when all costs are the same in uniform cost, it's just undistinguishable from DFS, from depth first search. And now here we have a differentiation. The lighter color means shallower water where you can go faster, and the blue and the darker one means deeper water when you go slower. So what is when we run this algorithm? Let's see what happens. So it still looks like DFS, okay? Like we are not we're disregarding the information of the depth here. And this one, let's watch this one here. Here you see that the shallowest nodes are favored, are explored before many of the darker or deeper nodes are explored. So this looks like a uniform cost. And this one is just BFS again, okay? It gives you, it reaches the goal, but the path is far from optimal, maybe far from optimal too. So what I want you to realize is that all these algorithms we have studied, the DFS, BFS, uniform cost, are practically the same, and you need to, and we implemented them in the same way. So the only thing we change is the data structure we use to enqueue the fringe, okay? So sometimes can remember that we still have a model, that we're operating on a model. That graph that we made is not the reality. It's just a simulation. It's just a model of the reality. And your search will always be only as good as your models. So models can fail. And in fact, sometimes they have done that in the famous maps in the earlier version of the navigators. I don't know if this is the Google or another navigator, but it can lead you to the water. It can give wrong results. So the only difference, remember, is that one I mentioned. And we will will get into the end of this slide. This is lecture 3. And at the very end, you see the tree search, which is a strategy. This is the pseudocode for the tree search strategy. And tree search is redundant because when you can be redundant, okay? Sorry. It can be redundant, but then why can it be redundant? Because you can go from Arad to, and when you expand many nodes, you go to CView, and then if you expand these nodes, you can go to Arad again, and so on. So this repetition is costly, and we can avoid that with in a very simple matter, in a very simple way. And the very simple way is just before we enqueue any node into the fringe, we exclude those nodes that have already been visited. Okay, that we have already seen that. This is what is called graph search. And I want you to make, once you have the slide, make a screenshot or have that slide up all the time. And let's go to the code, because this is the algorithm that you're going to actually write and program in the next project. And so just let's go over it. It's graph search accepts an object of a problem and a fringe. And the working is the following. We need to initialize an empty set, a set. In this case, it's named closed, and we will store all the nodes that have been visited, and we consider them closed. So they have been visited once, they are already closed. And in the fringe, we have all those nodes that are pending. Okay, so how do we initialize the fringe? Well, we need to have a function that tells us, here's a problem, you plug in the problem, and then the function somehow gives you the starting node and tells you, okay, this is the start node, and then you store it in the fringe. Then you have this loop in which the first thing you do is check if the fringe is empty, because if it is, then you return failure. But if it's not, if everything went okay, you should have at least one node, which is the start node. So you remove it from the fringe by popping here's the fringe. How are you going to store it? This fringe is going to be a LIFO or stack or a FIFO queue, and this remove front will be a pop from a stack, or a pop from a queue, or a DQ. And the goal test, then we have a goal test. We should have a goal test which is provided by the model. And so we plug in a state, the state which is removed from the fringe, and check if it's a goal. If it is a goal, then we return. What we need to realize is that in the problem you're going to code, you will not return the node, but you will return the path to the node. Including the node, okay? The goal node. Path from S to G, okay? This is what you need to output. Then if the, but if it was not the goal, then you need to say, okay, this state, I need to see if I have already seen it or opened it. And so you check if it is in set closed. And if it's not included in this set named closed, then you include it, you add it. And then you, after just adding that, you will expand all you should have a function to allow you to expand a state. That means get all the successors from that state and then just insert all those successors into the fringe until you're done with all the successors, and go back and then get an element from the fringe. Here, if fringe is empty, return failure, but if it has elements, then remove the front, whatever it is. If it's a LIFO, it will be in one end. If it's a stack, it will be in the other end. So you need to see what is this strategy. Now, how does that look in, how would we do that in the code? I'd like you to join me in the following. So let's see, I will share screen here. Okay, okay, sorry. I need to add a battery to this device before it dies. Sorry, it'll take a few seconds to plug a charger into one of the devices because it's so intensive. Charger. Seems like I lost the charger. I'll find it. But I wonder, please let me know if you, let me just turn this on. Let me know if you can see if there's anything wrong with the video. Can you see, can you distinguish? Do I need to make it bigger, perhaps?
I can read it.
Okay, so let me make it a little bigger. Here we are. Okay, then even a little. So let me know if it's comfortable for you to see that. Okay. So first, there's if you follow the instructions in the if you go to the website to CS188 and into the description of the project P1, which is search, and you download the code, this is what you get. Now you're told that you should not modify all the functions. You should modify only those functions that are, let's say, one that's called search.py. These are the ones that you need to modify. We can know. Let's see if this works. Grep code. So you have a string telling you to insert code in search.py in 4 parts, and search agents also that would need to be modified. So that's the only 2 programs that you need to modify. Please do not modify anything else. It is very dangerous to change any code that is not the code where you're allowed to write. So then there's what you need to do is you need to explore that code, and you can explore that code, but there's two files that are worth exploring. The one is, for example, utils dot py util dot py. This is a utilities file, and you should know these functions really well, which means you need to explore them to read them. And as you can see, there's a class, a class defined for fixed random that gives you fixed random numbers, and but it gives them immediately. So also, if you can see that we have in line 134 the definition of a stack. So even if you have a choice of defining stacks, because Python has its own stack structure defined, I advise you to use this one, because you would get the adequate times and complexities and the adequate working compatible with the rest of the software. So if you need to define a stack, you define it from this class, from stack, and because you have all the functions you need, like push, pop, and it's empty. The queue also push, pop, and is empty. And even more important, the priority queue is not like the other priority queues. So this priority queue provided in util is not the same that you can find as provided by Python. It has the push operation, the pop operation, is empty, and if you modify the update one, this function is not existent. It does not exist in the Python's implementation for a priority queue. So you need to use it from here. And it not only has that operation, but it also allows you to do that in constant time. Okay, so access to the lowest priority item is done in constant time. I mean, so getting the minimum is a constant time. And it is the kind of priority queue that would give you the minimum. There's another version of the priority queue, which is defined over here. And it has only the a push and an init, but it has another a function. It takes a function. Well, there are some instances in which this might be useful, but not in this project. Counter is another thing you need to check. Maybe not in this project, but it's very useful to know what a counter is. It's a different counter, a different data structure. You should read all this text, all those comments, and become familiar with the code and familiar with all those options that you have. And then this is a method of this counter of a counter data structure, which is called argmax, which gives you the index of the maximum element. This will become very handy also in projects where we handle costs, or when we get into Markov processes. It's not for searching, let's say, but you need to become familiar. Normalize is also, again, if you have a vector and its elements do not add to 1, when you normalize that vector, then you get a new vector with components that add up to 1 and that have the same relation to each other. So read on all these functions that you need so that you can understand what goes on when you start beginning to code. So before you begin to code, read all this. You see the race not defined. What does it do? And it's basically a function that would tell you, that will give you a message, a failure message, that is when you have not defined when you haven't defined it. Have not defined the okay, let me see, what time is it? Okay. So what do we need to do about apart from that? So not all the code, but at least the first part of the code you need to explore from util.py. And also, if you want to learn a little bit of how the game is played, and is very recommendable, read on this one. Okay, you will have always the guide to tell you this is these parts are worth reading. So you need to know what is an agent, how are directions implemented, how what is a configuration, and what is an agent state, what's a grid, what's what's the functionality of a grid, because these you would use definitely in this project. This you shouldn't have to read, but it doesn't hurt, especially this one, like the one called actions. So, but you need to read before you even start coding. And when you start coding, you have remember that you can search the py. And so please start today to do that. And I want you to do to code the first, the DFS, the depth first search, and the depth first search. You need to do that in the following way. You need to have your screenshot. Let me change the share screen to general. So in the next minute, what would be your flow? Your workflow would be this. Okay. So you first go to this site, the CSC188, to the Berkeley site, get the this and start reading also the depth of search. These are the directions. Before you even code, I advise you to take note and even do this. Search functions need to return a list of actions that will lead to the agent, okay? So that's why I was telling you, whenever when we I don't know if you see my pseudocode, I have already copied it to a screenshot. So whenever I see return node, what I will do is I'll need to return a list of actions. And then another important note, use the stack queue and priority queue data structures provided in util.py. So then test the program. You can test these that it works in your, if this runs, you're sure that it will run in your setup. You may get a message, however, for a deprecated TK inter, and that, but disregard it. It's just a warning, and the programs will run. You may have to change, perhaps instead of Python, you should use Python 2 or another corresponding command that invokes the corresponding version of Python, which is 2.7. And you should try to find a solution for the tiny maze, for the medium maze, for the big maze. And it tells you when would you be able to, when would you succeed, okay? So the strategy is you need to first implement DFS, depth first search. That is, which data structure are you going to use for DFS? For depth first search, what is this? Are you going to use a stack or a queue? For DFS, you will use a stack. Okay, so then you need to follow, please follow. Your code should be close to what we saw in the sorry. The code should be close to what we saw in the pseudocode. Okay, if it's not close, I will not grade it because it means probably that you're copying it from the internet. And so try to code following this very closely. Okay, but each of you should be responsible of your own project. And so if you keep close to the code with and you take care of the, sorry, this is, to take this off. And you stay close to the directions in the in this website for the project, then everything will be all right. Okay, so I now need to quit. Are there any questions? We'll meet on Wednesday.